Welcome to BrainOmega. Today we're starting at the very foundation. What is natural language processing, or NLP? NLP is all about using computers to work with human language, the words we speak, write, and even type into search bars. Imagine you're looking at customer reviews on a travel booking site. For you and me, understanding a review like, "The hotel was clean and close to the city center," is easy. We immediately get the meaning, the sentiment, and even the subtle details. But for a computer, this is just a string of characters. That's where NLP comes in. It helps computers make sense of language so they can do things like analyze reviews, answer questions, or even translate your travel plans into another language. Every time you talk to a virtual travel assistant, get automatic recommendations for flights, or see hotel reviews summarized for you, you're using NLP in action. Let's take a quick look at how computers handle data. If you run a travel site, you probably have lots of tables of data, things like ratings or prices. Computers love numbers. Calculating the average hotel rating? No problem. But look at the review column. Suddenly, it's not so easy. Words are messy, full of context, emotion, and even sarcasm. For a computer, "This hotel was the bomb" could be confusing. Is that good? Bad? Explosive? Natural language processing is the set of tools and techniques that lets computers work with this complex, rich text data, turning it into something useful and meaningful. Where does NLP fit in the world of artificial intelligence? At the very top, we have AI, computers doing things we once thought only humans could do. Below that, we have several branches. Computer vision helps computers see and recognize things in images. Think of scanning your passport with your phone. Machine learning lets computers learn from experience, like predicting flight prices based on past trends. NLP is all about language, interpreting and generating text, just like a human. Whether it's answering your travel questions or sorting reviews, NLP is the technology that helps computers understand and respond in natural language. In a travel booking company, a data scientist might analyze sales numbers, website clicks, and yes, even text data like customer reviews. That's where NLP is so valuable. With the right techniques, you can turn thousands of raw reviews into actionable insights. What do travelers love most about your hotels? Where do they see room for improvement? NLP helps you find the answers hidden in the words. All right, let's see this in action with a little code demo. Imagine you're running a travel booking website. You have a table of hotel ratings, prices, and reviews from your customers. Let's load up some example data using Python and Pandas, which is a super popular library for working with tables of data. You can see here we've got 4 hotel stays with a rating, a price, and the customer's review text. Now, computers absolutely love numbers. Let's see how easy it is for a computer to calculate some stats. No problem at all. Calculating the average rating and the average price is super easy for a computer. But now let's try to do the same thing with our review text. What if we ask the computer to give us the average review? Oops! The computer throws an error because it has no idea how to take the mean of text data. For us, looking at the review, "This hotel was the bomb," is clearly a positive thing. But for the computer, it's just a string of characters. No meaning, no understanding, just confusion. And this is exactly why NLP is needed. Natural language processing gives computers the tools to work with words, not just numbers. With NLP, we can teach computers to figure out if a review is positive, negative, or even sarcastic. We can summarize reviews, analyze trends, or build chatbots to help customers in real time. The history of natural language processing is full of excitement, setbacks, and breakthroughs. Let's walk through the major eras, starting in the 1950s and traveling all the way to the present day. We begin in the 1950s, where the very first attempts at using computers for language focused on simple rules and pattern matching. One famous example is the Georgetown IBM experiment, where a computer was programmed to translate Russian into English using just a small set of words and some handwritten rules. This was the first machine translation demonstration, tiny by today's standards but groundbreaking at the time. Then, in the 1960s, something even more interesting happened. The first chatbot. Eliza, developed at MIT, could hold a simple conversation by matching patterns and giving rule-based responses. It was like talking to a computer therapist, sometimes a bit silly, but people were amazed. These early efforts were exciting, but they hit a wall. Language is messy, and simple rules just weren't enough. Researchers realized if computers were ever going to understand language, they'd need more than just patterns. That led to the next era, traditional NLP, starting in the 1980s. Suddenly, computers were getting more powerful, and new mathematical tools called probabilistic and statistical models entered the scene. Instead of just following rules, computers started to use data and probability. This meant they could analyze huge collections of text and start to spot patterns, like which words tend to appear together or how often certain phrases pop up in travel reviews. In the 1990s, a landmark resource appeared, the Penn Tree Bank. Linguists hand-labeled millions of words, creating a goldmine for researchers to build and test new models. At the same time, machine learning began to revolutionize the field. Now, instead of just writing rules, researchers trained models to actually learn from labeled examples, such as which reviews are positive or which questions customers are asking about hotels. By the 2010s, a new revolution was underway: deep learning. Instead of designing features and rules by hand, computers began to use neural networks, complex mathematical models that could learn directly from raw data. Recurrent neural networks, or RNNs, and later LSTMs, helped push NLP to new heights. Pow! But the real game changer arrived with transformers. Models like BERT and GPT could handle language in ways never seen before, generating realistic conversations, summarizing reviews, and even answering travel questions with incredible fluency. Today, these large language models are at the core of modern NLP, and research is moving faster than ever. So, to sum up, early NLP was all about rules. Traditional NLP was about statistics and machine learning, and modern NLP uses deep learning and transformers, each step built on the last, making it possible for travel sites, apps, and virtual assistants to handle language in ever more human-like ways. Now let's bring history to life and build our own version of an early NLP chatbot, just like Eliza, but specialized for travel bookings. This little bot is rule-based. That means it doesn't really understand what you're saying. Instead, it's like a super basic call center menu. It looks for certain keywords and then gives a fixed reply. Let's walk through the code. First, we have a function called Travel ElizaBot that takes whatever the user types and turns it into lowercase. This makes it easier to match words, no matter how they're typed. Now comes the heart of the bot, a set of if statements. Each one checks if the user's message contains a specific word. If you mention book or reservation, the bot says, "I can help you book your trip." Where do you want to go? If you type cancel, it gives a polite but canned response. "I'm sorry to hear that you want to cancel. Which reservation should I look up?" If you ask for a recommendation or say suggest, the bot asks, "What type of destination are you interested in? Beaches, cities, or mountains?" There are also responses for greetings like hello or hi, for saying thank you, and for asking about price or cost. If none of these words appear, The bot doesn't know what to do, so it falls back to, "Can you please tell me more about your travel needs?" Say, now at the bottom, we have a little conversation loop. The bot starts by greeting you and then waits for your input. If you type exit, quit, or buy, it ends the chat. Otherwise, it uses our rule-based function to generate a reply and prints it out. Let's try it out. I'll type, "Can you recommend a hotel in Paris?" The bot recognizes recommend and asks what type of destination I like. If I say I want to book a flight, it gives the booking response. If I ask how much does it cost, so it knows I'm asking about price. But if I type something it doesn't expect, like, "What's your favorite travel memory?" the bot can't handle it and just ask. Let's take a guided tour through the wide spectrum of NLP applications and techniques that we'll explore together in this course. You'll notice that NLP strategies can be grouped into two big families: classic approaches, which laid the groundwork for language technology, and modern methods, which are powering today's most advanced AI tools. For each one, we'll see how it's used to solve real-world problems in the travel industry, like understanding reviews, sorting messages, and even recommending trips. Starting with classic NLP, we begin with rule-based pattern matching. Here, computers simply look for specific words or phrases, following hard-coded instructions. Imagine a system that automatically flags phrases like "excellent stay" or "poor service" in hotel reviews. This is the essence of rule-based methods: quick, simple, but not very flexible. The next technique is machine learning with logistic regression. This method learns to sort text into categories based on examples. For instance, by showing the computer labeled emails, some are booking requests, others are complaints, it can automatically learn to separate new incoming messages and route them to the right department, saving time and improving customer service. Then we move to unsupervised clustering methods, such as k-means or LDA. Unlike rule-based or supervised techniques, clustering groups similar texts together without any prior labels. In a travel business, this could mean automatically discovering themes in guest feedback like clean rooms, helpful staff, or great location, without anyone needing to manually sort thousands of reviews. Transitioning to modern NLP, we reach the world of deep contextual models like BERT and other attention-based architectures. These models don't just look for keywords, they truly understand the meaning and context of each sentence. They can pull out specific information, such as guest names or travel dates, from a messy chat conversation, making it much easier to fill out booking forms automatically. Another leap forward comes with encoder-decoder models, such as T5 or BERT. These models are masters at transforming or summarizing text. For example, they can take a lengthy guest review and generate a concise summary, giving hotel managers quick insights without reading every word. Generative models like GPT are the creative writers of the NLP world. Not only can they answer travel questions and write emails, but they can also craft entire personalized trip plans based on a customer's interests, producing content that sounds naturally human. Finally, there are embedding models like Mini-LM, which take language and turn it into numbers that computers can compare. This allows a travel site to recommend similar destinations or group together articles and reviews about related topics, making search and discovery a breeze for users. As you can see, every one of these NLP techniques, from classic pattern matching to modern generative AI, serves a practical role in the travel business, transforming unstructured text into valuable insights and powering user-friendly digital experiences. By understanding each approach and where it fits, you'll be equipped to build smarter tools, for your own applications and understand the magic behind the technology you use every day. We're going to explore how approaches to natural language processing have evolved generally over time in terms of architecture, from early methods to today's most powerful techniques. Let's begin with one of the earliest and most influential, the TF-IDF approach. TF-IDF, which stands for Term Frequency Inverse Document Frequency, is a classic statistical technique that helps us understand which words are most important within a single document compared to all the other documents in a collection. Using TF-IDF, we can convert words and sentences into numbers, creating a mathematical representation of language that computers can process. Once our text data is in this numerical form, we can use machine learning methods like the Naïve Bayes classifier to categorize reviews, messages, or emails. We can even combine TF-IDF with clustering algorithms like k-means, which allows us to automatically organize large collections of travel reviews or customer feedback into common topics. However, TF-IDF and similar approaches have their limits. They only pay attention to how often words appear, ignoring the order of words and the actual context in which they're used. This means these methods can't fully capture the meaning of sentences, and they certainly can't generate new text like answering a question or writing a summary, things we expect from modern NLP systems like ChatGPT. As computers became more powerful, thanks in part to advances in graphical processing units or GPUs, researchers were able to train deeper neural networks such as recurrent neural networks or RNNs. RNNs are better suited for handling sequences because they can pass information from one word to the next, allowing them to model temporal relationships in text. But RNNs also have significant drawbacks, especially when it comes to learning long-range dependencies in language. They often suffer from problems like vanishing or exploding gradients, which makes training these networks extremely difficult. To overcome these issues, the long short-term memory, or LSTM, architecture was developed. LSTMs are a major breakthrough because they are much better at remembering important information over longer text sequences and help prevent vanishing gradients. However, even LSTMs have challenges. They are still slow to train, use a lot of memory, and struggle to capture relationships between words that are far apart in a sentence or paragraph. They also can't take full advantage of parallel processing since they process text one step at a time. This brings us to the modern era of NLP and the rise of the transformer architecture. Transformers, thanks to their self-attention mechanism, can model long-range dependencies in text much more effectively and efficiently than previous approaches. They can process entire sentences or even documents at once rather than word by word, allowing them to capture the global context and relationships between distant words. This makes them ideal for a huge range of tasks, from classifying travel reviews to clustering customer feedback to powering advanced applications like ChatGPT that can generate natural, human-like language. So, as you'll see in the upcoming chapters, our focus will shift towards understanding how transformers work, step by step, and why they have become the foundation for the most powerful NLP applications today. Let's dive in and unlock the secrets behind this groundbreaking technology. When starting an NLP project, the very first thing you'll do is define your objective. It's just like planning a journey. You need to know your destination before you can set out. For example, imagine you're working with a travel company and your goal is to automatically identify and summarize guest complaints from thousands of hotel reviews. Getting this objective crystal clear will guide every other step you take. Once you know what you want to achieve, the next step is to collect all the text data you'll need. For a travel business, this might mean pulling in recent reviews from your booking platform, exporting chat logs from your customer service chatbot, or even gathering feedback from survey responses. Sometimes you'll combine data from different sources to get a complete picture of what your customers are saying. With all your raw data in hand, it's time to clean things up. Real-world language data is often messy, filled with typos, duplicates, missing information, or strange formatting. At this stage, you'll remove errors, standardize the format, and make sure you're only working with high-quality, useful text. Now comes the step that's unique to NLP projects: text pre-processing. Human language is full of quirks, so before a computer can understand it, we have to prepare it carefully. This often means converting everything to lowercase, removing special characters and common words that don't add meaning, like the or at, and breaking sentences into individual words or phrases. You might also want to reduce words to their base form, so traveling and traveler are recognized as the same root. This turns a messy review like "I absolutely loved the breakfast" into a simple, analyzable format like "love breakfast." With clean, pre-processed text, you're ready to explore your data. This is the part where you get curious. What words come up most in negative reviews? Are there clusters of complaints about cleanliness, noise, or staff behavior? You might make charts, word clouds, or group feedback into topics, helping you spot patterns that will guide your next steps. Next, you'll build and refine models to answer your original question. Maybe you train a classifier to label reviews as complaints or compliments, or use clustering algorithms to discover hidden themes in guest feedback. You might even experiment with different types of machine learning models, from straightforward logistic regression to cutting-edge transformers, adjusting your approach based on what works best for your specific data. The final step is to share what you've learned. This could mean presenting your findings to hotel managers, building a dashboard to track trends in real time, or even deploying your model so it automatically alerts staff when a new complaint is detected. The value of your work comes from turning language into clear, actionable insights that others can use. Remember, this process is rarely one way. As you go through the workflow, you'll often find yourself looping back. Maybe you discover a new kind of feedback you hadn't considered, or your model reveals a data quality issue you need to fix. This kind of iteration is normal and helps you build robust, real-world solutions. In summary, the NLP workflow is all about moving from messy raw language to valuable, data-driven answers step by step. Whether you're sorting reviews, building chatbots, or extracting key details from messages, following this structured approach will help you deliver real impact in any business, especially in fast-moving industries like travel. Now, let's dive deeper into the crucial phase of text pre-processing, an essential bridge between cleaning raw data and modeling it effectively. Think of this as preparing your raw guest reviews or booking messages to be machine-ready so that the computer can actually understand and analyze them. The first step in this preparation is lowercasing. This means converting every letter in your text to lowercase, so words like hotel and hotel are treated as the same. It may seem simple, but it avoids confusion and redundancy in later analysis. Next, we remove special characters. Customer feedback often includes punctuation marks, emojis, or other symbols that don't add meaning for our model. Using tools like regular expressions, we strip out these characters so the text is cleaner and easier to process. After cleaning, we move on to tokenization, breaking down sentences into smaller pieces, usually words or sometimes phrases. For example, the sentence "great location and friendly staff" becomes a list: great, location, and friendly staff. This is the basic unit the computer works with during analysis. To reduce complexity, we apply stemming or lemmatization, which means converting words to their base or root form. So words like traveling, traveled, and traveler all become travel. This helps the model recognize that these words are related, which improves accuracy in tasks like sentiment analysis or topic detection. An important step is filtering out stop words, common words like the, is, or at, that don't carry much useful information. Removing these words helps the model focus on the meaningful parts of the text that tell us what the guest really thinks. Sometimes we use parts of speech tagging, which labels each word with its grammatical role, whether it's a noun, verb, adjective, and so forth. This gives more nuanced information about the structure and meaning of the sentences, which can be useful in advanced NLP tasks like named entity recognition. Once the text is cleaned and normalized, we need to convert it into numbers because machine learning models work with numerical data. One common method is creating a document term matrix where each document, like a review, is represented by the frequency of each word it contains. This is often called the bag of words model since it counts words without considering their order. Building on that, we use TF-IDF, or term frequency inverse document frequency, which is a smart extension of the bag of words. Instead of just counting words, TF-IDF weighs each word by how important it is, giving more emphasis to words that are frequent in one document but rare across all documents. This helps the model focus on words that truly distinguish one review from another, improving classification and clustering performance. By carefully following these pre-processing steps, cleaning, normalizing, tokenizing, and vectorizing, you transform messy travel reviews or messages into a structured format. This clean, numerical representation forms the solid foundation for any machine learning or deep learning model you build next, whether it's predicting customer sentiment or summarizing trip feedback. Let's carefully walk through this text pre-processing pipeline tailored for travel reviews using Pandas and NLTK. We start with a sample data set of hotel reviews, each with a rating, price, and raw review text. Notice the text contains uppercase letters, punctuation marks, and even an emoji in one of the reviews. Our goal is to transform these raw reviews into a clean and structured form for machine learning. Step 1. Lowercase conversion period. The first transformation converts all text to lowercase. This simple standardization step ensures that words like hotel, hotel, and hotel are all treated the same. Without this, the model might mistakenly think they are different words, increasing the complexity unnecessarily. In the output, you can see the new column cleaned to review where every letter is lowercase, like great location, very clean, instead of great location, very clean. Step 2. Noise removal. Next, we remove punctuation and special characters using regular expressions. This means that exclamation points, commas, and emojis, like the smiley face, are stripped out, leaving only letters and white space. This step is essential because punctuation often does not add value for text classification or clustering models. In the processed output, the clean review column now contains text free of these symbols. For example, great location, very clean, without commas or exclamation points. Step 3. Tokenization. Then we tokenize the clean text, breaking each review sentence into individual words or tokens. This converts a string into a list of words. For instance, the sentence "great location, very clean" becomes "great location, very clean." This breakdown makes it easier to analyze the frequency and meaning of individual words rather than the entire sentence as a whole. Step 4. Stop word removal. We then remove stop words, which are common but usually uninformative words like the, was, and, or very. Removing these helps the model focus on the key descriptive words. In the output column tokens no stop, you can see the token list is now shorter and more meaningful. For example, great, location, clean without every. Step 5. Lemmatization. Finally, we apply lemmatization to reduce words to their root forms. For example, staying, stayed, and stay all become stay. This normalization reduces the vocabulary size and groups related word forms, improving model efficiency and accuracy. In the lemmatized column, tokens like hotel, bomb, or worth price represent these root words ready for analysis. Optional step, part of speech tagging. While not shown in this exact code snippet, POS tagging assigns grammatical roles to words such as nouns, verbs, or adjectives, which can further enhance model understanding, especially for complex NLP tasks. In this updated version of the code, we use Pandas' built-in str replace method with regular expressions to clean the text. This approach is more concise because it allows us to apply powerful pattern matching and replacement directly on the entire column in just a couple of lines without needing to define a separate function. Because Pandas operations like str replace are vectorized, they process all rows in the data frame at once, which is typically faster and more efficient than applying a Python function row by row. This not only makes the code cleaner and easier to read, but also improves performance, especially when working with large datasets. In contrast, the earlier version used a custom function with re.sub applied to each row via .apply. While this works fine, it is more verbose and can be slower because it calls a Python function for each individual review instead of leveraging Pandas' optimized string operations. So, using Pandas' vectorized string methods with regex helps us write cleaner, more maintainable code that runs faster, both important factors when pre-processing large amounts of text data in real-world NLP projects. We begin by importing the key Python libraries. Pandas is used to store our reviews in a structured, table-like format. The RE and Unicode data libraries give us tools for cleaning raw strings, handling punctuation, and normalizing messy Unicode characters like accents and emojis. From the NLTK toolkit, we load stopwords, WordNet, and the WordNet lemmatizer, which are essential for filtering and reducing words to their base form. Next, we prepare the necessary NLTK resources. These downloads are like dictionaries and models that NLTK needs to tokenize text, recognize stopwords, lemmatize, and assign parts of speech. For example, Punkt allows NLTK to split text into sentences and words, while stopwords provides a curated list of common filler words such as the or is. The WordNet resource supports lemmatization, ensuring words like running and ran are reduced to the root run. Finally, the average perceptron tagger provides part of speech tagging, labeling each token as a noun, verb, adjective, and so forth. Our sample dataset is a miniature version of what a travel company might collect. Each row contains 3 types of data: a numeric rating, the price of a booking, and a written review. This mix illustrates why pre-processing is important. Numbers are straightforward for computers, but the free text reviews are messy, subjective, and full of variations. For instance, a review like "This hotel was the bomb" combines slang, punctuation, and even an emoji, all of which need to be normalized before analysis. We also add a configuration toggle to decide whether or not digits should be removed from reviews. This is a practical design choice. In some applications, numbers like room 305 or open 24/7 provide meaningful information. In others, numbers can act as noise. By keeping this step optional, the pipeline remains flexible for different business contexts. To handle messy text, we define a few helper functions. The Unicode normalization function ensures that all characters are consistent, by decomposing them into base characters, stripping away accents, and recomposing them into a uniform format. This guarantees that words like cafe and cafe are treated the same. Another helper function handles contraction expansion. Human language is full of shortcuts like it's or I'm, but for modeling, it's better to expand these to it is and I am. This reduces vocabulary size and keeps the meaning clear. Finally, we also set up functions for mapping part of speech tags into WordNet categories and a small illustrative normalizer that strips off common suffixes like -ing or -ed. While basic, these functions demonstrate how we can standardize words further to capture their root meaning. Through this setup, we're equipping our pipeline to tackle every stage of text cleaning and normalization. From Unicode normalization and contraction handling, the removal of punctuation, stop word filtering, lemmatization, and part of speech tagging. Each of these steps transforms chaotic raw reviews into structured, machine-readable data that can fuel tasks like sentiment analysis, clustering, or automated travel recommendations. The first step in our pipeline is Unicode normalization and lowercasing. Raw text often contains accented characters, emojis, and formatting inconsistencies. For example, the word cafe and cafe should be treated as the same. By applying Unicode normalization, we break down characters into their base form, strip away unnecessary accents, and then fold them back into a standardized format. After that, we convert everything to lowercase. This ensures that words like hotel, capitalized first letter, normal word, hotel, all lowercase, and hotel, all caps, are considered identical during analysis, avoiding artificial duplication in our vocabulary. The second step is contraction expansion. Human language is filled with shortcuts. Think of phrases like it's, don't, or I'm. While convenient for writing, contractions increase the number of unique tokens in the dataset. Expanding don't to do not and I'm to I am reduces this variation and makes it easier for downstream models to capture meaning. In practice, this is done using regular expressions that replace contracted forms with their expanded equivalents. The third step focuses on removing punctuation and symbols. Reviews often include exclamation marks, question marks, emojis, or decorative characters. For example, the hotel was amazing. Contains symbols that don't add much analytical value. By stripping these characters with a regex replacement, we simplify the text without losing its meaning. This step also improves tokenization later by ensuring that we only split meaningful words. In the fourth step, we optionally remove digits. Numbers can either be useful or distracting depending on context. In some reviews, a number like room 101 might matter, while in others, 24/7 is just noise. Our pipeline makes this configurable by default, removing all numeric digits to keep the text clean. Next, we apply whitespace normalization in step 5. After all the replacements above, reviews might contain multiple consecutive spaces. By collapsing these into a single space and trimming edges, we ensure that the text is tidy and uniform. This makes tokenization more reliable and avoids generating empty or meaningless tokens. Step 6 introduces tokenization. Here, each review is broken down into individual words or tokens. For instance, great location, very clean becomes great location, very clean. Tokenization transforms continuous text into discrete units that we can analyze or model further. The seventh step is stop word removal. Stop words are common words like the, was, or and that don't carry much meaning. Removing them helps focus the analysis on the words that matter most, such as location, clean, or price. This reduces noise and improves both efficiency and model interpretability. In the eighth step, we add part of speech tagging. Each token is labeled with its grammatical role, noun, verb, adjective, and so on. For example, loved would be tagged as a verb, while hotel would be tagged as a noun. This linguistic information can enrich models by distinguishing how words function in context, making tasks like sentiment analysis more precise. The ninth step applies lemmatization with part-of-speech guidance. Unlike simple stemming, lemmatization reduces words to their base dictionary form while respecting their grammatical role. For instance, better becomes good as an adjective, while running becomes run as a verb. Using POS tags ensures that words are lemmatized accurately instead of mechanically chopping off suffixes. This produces cleaner, more semantically meaningful tokens. Finally, the 10th step creates convenience columns to make analysis easier. We rejoin filtered tokens into cleaned text for quick viewing, and we apply a small Naïve normalizer to strip off common suffixes as an illustrative step. These columns provide both human-readable and machine-friendly versions of the processed reviews, making it simple to compare raw text with its cleaned and normalized counterpart. We began our journey with a simple question: what is natural language processing, or NLP? At its heart, NLP is the bridge that allows computers to work with human language. The reviews we write, the questions we ask, even the casual expressions we use in everyday life. From the start, we saw how easy it is for humans to understand a review, like the hotel was clean and close to the city center, while for a computer, it's nothing more than a string of characters. That's where NLP comes in, transforming those characters into meaningful insights. From there, we explored the wide range of NLP applications and techniques. We looked at traditional approaches like TF-IDF and Naïve Bayes, which paved the way for early breakthroughs in text classification and clustering. We then moved into more advanced methods such as recurrent neural networks and LSTMs, which added the ability to capture sequences and dependencies in language. And finally, we arrived at transformers, the architecture behind modern large language models like BERT and GPT, which allow machines to understand context, semantics, and even generate human-like text. We also connected NLP back to the broader data science workflow, showing how NLP projects fit seamlessly into the same pipeline as any other data-driven task. The only key difference is the extra pre-processing step, where raw text must be carefully cleaned and normalized before it can be modeled. This led us to dive deep into the pre-processing pipeline itself, step by step, converting text to lowercase, expanding contractions, removing punctuation and digits, normalizing Unicode characters, tokenizing sentences into words, removing stop words, applying lemmatization, and even adding part-of-speech tags for richer context. By the end, we transformed messy, inconsistent text reviews into clean, structured tokens that are ready for machine learning. So, from understanding the big picture of NLP to breaking down the nuts and bolts of pre-processing, we've laid a strong foundation for everything that follows. These are the building blocks of real-world NLP applications, from chatbots and recommendation systems to sentiment analysis and intelligent search. This concludes the first part of our tutorial series. If you found this journey helpful, make sure to like the video, subscribe to the channel, and turn on notifications so you don't miss the next lessons. Thanks for learning with us, and I can't wait to see you in the next part of the series.